Hi all. So today we are going to learn the output equation of three-phase transformer. In the last video we have learned the output equation of a single-phase transformer. So same as our single-phase transformer, we can derive the output equation of a three-phase transformer. Most of the steps are same. Okay. So this is a cross section of a quad type three-phase transformer. So for a three-phase transformer, three limbs will be there, and we are placing the three windings in these three limbs. Okay, in every limb we are having a low voltage winding and high voltage winding. Always the low voltage winding is wounded just around the core, and above the low voltage winding we are winding the high voltage winding. Okay, so there will be two windows. Okay, there will be two windows for a three-phase core type transformer. Okay, so these windows will accommodate the windings. Okay, mainly the windings. So we are starting the derivation steps as in the case of a single phase transformer. That is, we are starting from the EMF equation, that is E is equal to 4.44 FIMT. Okay, F is the frequency and FIM is the flux, and T is the number of turns. Okay, so the EMF per turn, if you want to find the EMF per turn, that is E suffix small t, it will be equal to and induced EMF by number of turns t, E by t. So EMF per turn will become 4.44 FIM. Okay, and in the case of a three-phase transformer, actually each window has two primary and two secondary windings. Okay, so here each window has two primary and two secondary windings. Okay, so actually the window space factor, okay, KW. So KW will be the ratio of conductor area in window by total area in window. So the conductor area is represented as AC and total area is represented as AW. So from that, the conductor area in window AC is equal to KW into AW. Okay, so this is not as the first equation, that is 4.16. Okay, this equation we need for the derivation steps. Okay, and next one, the current density in the windings. Okay, same as our single phase transformer, the same steps we are following here. That is, the current density delta is equal to IP by AP, which is equal to IS by S. That is, in the both in the case of primary and secondary windings, in both sides the current density will be same. Okay, and from that AP is equal to IP by delta and IS equal to IS by delta. And also we know that for a transformer, if we are neglecting the magnetizing MMF, the primary and secondary MMF will be same. That is, primary and secondary ampere turns will be same. Okay, so IP into TP is equal to IS into TS. We can denote as AT. That is capital AT. Okay, both are same. So we can replace each and every, that is primary and secondary MMF with the term AT. Okay, capital AT. And here it is the equation of total copper area in window AC. Okay, also after finding this AC, we are just comparing our equation with our previously find AC. So that is the design step, actual steps in derivation. Okay, so here AC can be found using the equation that is total copper area in window. So we have to add that copper area in the case of primary winding plus the copper area in the case of secondary winding. But we know that in the three-phase winding there will be two sets of primary and secondary winding. Two sets of primary and secondary windings will be there. Okay, so we have to multiply the term with 2. Okay, so 2 into number of primary turns into area of cross section plus 2 into number of secondary turns into area of cross section. Okay, so 2 into TPAP plus 2 into TSI AS. Okay, here AP is the area of the primary winding, and that is cross section area of the primary winding, and AS is the cross section area of the secondary winding. Okay, TP and TS are the turns on both primary and secondary. Okay, and we can use the equation of IP by delta for substituting AP and IS by delta for substituting AS here. Okay, so we are taking outside the 2 by delta common, so it becomes TPAP plus TSIS, and we know that the primary, this is the MMF. Okay, that is a primary MMF and secondary MMF. So the primary and secondary MMF are same. We can replace it with the term AT. So AT plus AT. Instead of this TPAP, it is AT. Instead of this TSIS, it is also AT. So it becomes 2 into 280 by delta. That is 480 by delta. That is, AC will be equal to 480 by delta. So we are going to compare this equation with the 4.16 equation AC. Okay, both are conductor area in window. So by comparing that, 480 by delta will be equal to KW AW, and from that 80 will be equal to KW AW delta by 4. Okay. And we know that the kVA rating of the three-phase transformer, okay, that is Q is equal to 3 into volt ampere per phase into 10 raised to minus 3. That is 3 into Vp Ip into 10 raised to minus 3. That we know. Okay. And here actually the Vp is approximately equal to Ep. Okay. If you are collecting losses, it will be approximately equal to Ep. So 3 into Ep Ip into 10 raised to minus 3. If you are multiplying and dividing this term with the Tp, okay, what will happen? Here it becomes Ep by Tp and Ip into Tp. Okay, so this Ep by Tp we can replace it with the term Et, that is EMF per turn. In the starting slide we have learned that is Et is equal to E by the total number of turns. Okay, so likewise here this Ep by Tp will be equal to Et, EMF per turn. Okay, and Tp into Ip is equal to our ambitance At, capital At, that is Tp and Ip. Okay, both are 80, so it is 80. So Q becomes 3 into Et into 80 into 10 raised to minus 3. So we have to substitute the values for Et and At here. Et we know that Et is equal to 4.44 FIM, and At we know that it is KWAW delta by 4. Okay, so by substituting that values we will obtain like this, and by just rearranging and cancelling some terms we will obtain it as 3.33. that is our Q as 3.33 FIM KWAW delta into 10 raised to minus 3. Okay, and also we can replace this phi m. Okay, that is Bm is equal to phi m by Ai. So phi m is equal to Bm into Ai. So instead of this phi m we are substituting this Bm into Ai. Okay, so the last equation, okay, that is the output equation Q. Okay, output equation of a three-phase transformer Q will be equal to 3.33 FBM into AI into KW AW delta into 10 raised to minus 3. So that is the output equation, and here note that AI means actually it is the net core area. Okay, sometimes it may be given in the question itself. So you have to learn the output equation of both the single phase and three phase, and each and every steps are almost the steps are same. Okay, so I hope it's clear. So thank you.